Welcome to Computer Vision Decoded, where we help you make sense of the quickly evolving world of computer vision. Today, I'll be joined by Jared Heinley and a special guest, Itzik Ben-Shabat. Itzik has a PhD in computer vision, and he is a visiting research fellow at the Australian National University and Technion, Israel Institute of Technology. And he also hosts his own podcast, Talking Papers, where he talks to first authors on research papers about computer vision, machine learning, AI, and other topics related to what we're talking about today. In this episode, we're going to dive into implicit neural representations. That might be a topic that is new to most of you, but is quickly evolving and something that you should be very aware of. And always, at the end, I'll make sure I include links to everything we discuss in this episode so you can dive in deeper in your own research. Now let's get to this episode. Welcome, Itzik, to our latest episode of Computer Vision Decoded. Today, we're going to talk about implicit neural representations. And for Jared and I, this is new territory, at least for me. Jared may have run into this in his past studies, but it is a field that neither of us work in day to day. And we're really excited to have you on this episode. So welcome, Itzik.
Yeah, thank you very much for having me. I'm always happy to share knowledge and research.
All right. So just to start out this episode, I'm assuming that a lot of our audience may have heard of implicit neural representations. They may know a little bit about it, but I'm actually going to assume most people know nothing about it. So just to start out the groundwork of what we're going to discuss today, can you just from a very high level explain what this technology is? What is implicit neural representations?
Yeah, okay. So basically, implicit neural representations aim to take, basically any input signal, but for example, an image or a shape represented as point clouds, or even an audio signal, and encode that into a neural network, right? So you have usually, like sometimes these are called coordinate networks. So you take an input coordinate and you output the signal that you want. So if it's an image, you take the pixel, your output is the pixel color. If it's a point cloud, you take a point in space, you say, is it on the surface or not? So it's like this way of taking these different type of signals and encoding them into a network.
Okay. So it does not necessarily have to be, we've been primarily talking about 3D objects and visualizing 3D models. So it can cross into audio, video, all sorts of representations.
Yes.
Okay.
So my main focus in this domain was obviously working with shapes because I work in the 3D domain a lot, but many papers have shown that it's not exclusive to that. I think it has a lot of very interesting applications in this 3D domain because unlike the other domains, it doesn't really just encode the input. It kind of has some, I would say, generalizability option because, if we're talking about points, right, point clouds, they're actually samples of something that's more continuous, right? And when you learn this implicit neural representation, you're actually getting something that is continuous again, unlike an image where you encode an image, so you still get something that's more discrete as output because you always sample it. It is more continuous in some senses, but I think for point clouds, you're moving from the point domain to kind of the surface representation of things.
Okay,
that makes sense. And just you talked about 3D, which we love to talk about here. How does when you think about an implicit neural representation, how does that compare and contrast to something like a NeRF? We've talked about NeRFs, on this podcast before, saying, it's a way for a machine learning model to, represent, a 3D scene so that you can then render it from, different viewpoints. Are these the same tech? Are we talking about the same thing here? Is this something different?
Yeah, that's a great question. So I think they're complementary in some levels, right? Because NeRFs, right, you're encoding the space as like a neural field, right? So you want to encode the shape, and you have the density that kind of encodes the, sorry, you encode the color, and you have the density that kind of encodes the shape. And there are new works popping up that kind of try to combine these two ideas into this one framework. And it seems like each of them has their own benefits, right? Because the NeRFs are very great at creating these very reliable kind of novel view synthesis outputs, and the results are amazing and smooth and kind of really, when you look at those NeRFs, they blow you away. But if you kind of look closely at the results as to the fidelity of the geometric reconstruction, you see that at least currently, I don't know, maybe tomorrow it wouldn't be correct anymore, but at least currently there are still issues to solve there to kind of get like this high level of detail that you would expect from a surface, right? In the world, right? Things are tend to be smooth; they're not like jaggedy or wobbly. Where all of these kind of NeRF based, I would say, combos of implicit neural representations and NeRFs, they still have these kind of challenges that need to be resolved.
Okay. I think that makes sense. That's a good point. So like, so where NeRFs are geared toward visualization, and being able to render, a nice, beautiful photorealistic representation. They, NeRFs don't necessarily care about that underlying geometry. Whereas you're saying that's where, with an implicit neural representation, if it's trying to represent the underlying signal or the underlying data there, the geometry or the audio or whatever that data or signal is, it's focused on, the shape, the geometry, the thing that, and not necessarily just generating a pretty picture.
Yeah, exactly. This is why it's mostly used in like, it's evaluated, like the implicit neural representations, or we can call them INR for short. They're mainly focused on, in 3D, on surface reconstruction. So you evaluate how well it captures the underlying shape. Whereas in NeRFs, as you said, it's more geared toward getting like this nice view that you can tell if it's true or not, but the underlying geometry may not be. And this is why all the NeRFs, they have different challenges when it comes to transparent objects, right? It creates these kind of fuzzy, kind of fake artifacts just to fool your eye. But if you look at it from a different angle, you can see that um, that fuzziness. In INRs, it's a different problem. It's very focused on the reconstruction quality.
All right. And I do like how we're now going to reference this as INR for the rest of the episode because it is quite a mouthful to say. And I do like the point you're saying. It's we're representing a shape, and so I think of audio too. I think that's a hard one for people to think of. How can some technology work for 3D reconstruction in audio? Well, we're reconstructing the shape of a waveform, things like that. So I think it's very interesting how this technology is. You could go into this in a completely different focus than we're going to talk about today. So what got you into this field? What got you into this line of research?
Oh, wow. That's a good question. So I've always been, okay, so this actually goes back a long, long time. And I will tell you, like, this is my origin story. I'm actually a mechanical engineer by training, and I used to do mechanical design. And there was one place that I was working at where we used to scan objects. We had like this big, expensive 3D scanner. This is, I don't know, maybe over 10 years ago. We had this big, expensive 3D scanner, and we used to scan objects. And the reason why we scanned objects is because they had this complicated geometry, and we wanted to, design something that would kind of mount onto that or kind of latch or some, and it wasn't easy to measure with traditional tools. And then we got this big point cloud, and the software that existed back then were really primitive. Like, you could do some basic surface reconstruction, but it would never like do exactly what you want. And that's how I generally got into this whole domain of doing point cloud processing for different reasons, because I wanted to invent that button that you just press that button and you get like this perfect reconstruction. And when I say reconstruction, I also, in my head, it's still like the mechanical engineer view of reconstruction. I want to get the extrusions, where the holes go, where the drills, when is it a screw, where is it just a rivet. And that's kind of what led me down this path initially. And specifically, like, in the domain of implicit neural representations, I had some work that I've done a lot of normal estimations, right? So there are very, very classical methods to do that. And as I think it was around 2017, 18, I was midway through my PhD, and I really liked how you can use all of these deep learning methods to kind of solve these traditional problems like normal estimation. But in the bottom line, normal estimation is almost surface reconstruction. So the next thing was, okay, let's take all of these powerful tools and see how we can use them to do that surface reconstruction. And I admit I wasn't the first one. Like I think DeepSDF is one of the papers that kind of started this. Also, occupancy network. There are a few papers that kind of started this implicit neural representation kind of trend. But implicit representations per se existed even before that, right? We just guessed the functions that we want to use. And the main thing here is, okay, let's learn those functions. We don't need to guess them anymore. Like we can just learn them.
All right. So there's a couple terms that you threw out there that I also feel like our listeners may have get lost. Can you explain what just you're talking about normals, normalization? That's a really basic term for me, but I also know that a lot of people who may be listening might not quite understand what you mean by that.
Yeah, I'm happy to. So normal estimation, basically, when you look at a point cloud, right? So this point cloud represents an underlying surface. So the normal is basically the normal to the surface, right? So if you walk on the surface, imagine you have a little Lego person walking on that surface, where is his head, right? What's pointing up? That's the normal vector. And normal estimation basically means given a point cloud, right? Every place on that point cloud, where is up? Where is the normal direction of that surface? And the reason why it's so important, like it has numerous applications, right? If you want to kind of understand how lighting would bounce off a surface, that has a lot to do with the normal. And many other, like if you want to align it to other things, right? If you want to do like a registration kind of problem, or normals are very crucial in many applications.
Okay. Yeah, I was thinking of it as you have a point cloud. We have no idea what the front of each point is, which way is that point looking. So that definitely helps. And I think I learned very early on from Jared actually a lot about normals, and a lot of times I'll have a point cloud and it has no normals, and learning what's the best way to deal with that data if I want to turn it into a surface. That definitely helps. And I know there's a lot of different choices you can make in algorithmically figuring out which way, estimating the normals if you don't have that. But a lot of software nowadays, if you're capturing a point cloud with a LiDAR scanner with photogrammetry, a lot of times the normals are already kind of not baked in, but it comes with the data you have. But I don't know how many times they'll get a data set and it's been stripped of those, so you have to deal without that. And I'm kind of hinting towards what your last year's work is about. So interesting. So okay, so now you're in this. We're looking at you're looking at INR for reconstructing scenes, objects. You've fallen in that line of work, so you're talking about this deep SDF. There's some other past projects. If someone wants to kind of jump into the journey and work their way through to what you were working on the last couple of years, is there any prior work you'd have them look at, that you'd have them read, or just watch? I always like to watch the project papers from CVPR or one of those conferences that kind of gives you a 2.5 minute overview. Is there any if you were recommend someone go find 3 different projects or 3 different videos to watch, is there any topics that you think would give them a good base beyond what we talked about today?
Yes. So I think the very first place to start would actually be not related to the neural side of the implicit neural representation. That would be Poisson surface reconstruction, right? It's an industry standard by now. Everybody uses Poisson surface reconstruction. I think this is like a good place to start if you're completely new to this problem or domain. You kind of have to know Poisson surface reconstruction. The next 2 are DeepSDF and occupancy network, which came out the same year. They're just tackling the problem in a little bit of a different way. But the reason I think they're a good place to start is like they basically kind of started the trend. So everything is very self-contained in those papers that you can follow along and read through fairly easily. And actually, DeepSDF has a nice website and implementation that everybody can download and use on GitHub. So it really is a good place to start. Yeah.
Yeah, that's a great. See, I'm trying to if I can bring up one of those pages on the screen here. I know that Deep SDF is I believe is connected with Facebook, and they do a pretty good job at visuals. And because I know that a lot of people jump into this just wanting some visuals to help understand. That's how I tend to start. Look at the pretty pictures.
Of course.
Get a base understanding. Yeah. Especially if, I'm sure Jared looks through CVPR papers and half of it he's lost because it can get quite, in the minutia of details. And if you haven't been following that line of research for a while, I'm sure a lot of it goes right over your head. So we start with the pictures, ask some questions maybe. All right. Okay. So, Jared, do you have any specific questions so far about what he said?
Yeah, well,
before we move on to his research that he's been working on lately.
Yeah, one thing I kind of wanted to go back and just probe a little further on was just understanding, like you mentioned there about, so we have implicit neural representation. So what if you just drop that neural part? What is an implicit representation? Going from, I'll stop there. What is an implicit representation just by itself?
Yeah. So the way I like to think of it, if I kind of try to break it down to the building blocks, right? It's basically how would you represent a shape if you only had like one function that you can use to represent it, right? And I think the easiest example is a surface, right? If you have like 4 parameters that you set, you can define any surface in space, right? Or a sphere, for example, right? You know where the center of the sphere is, you know where the radius is. You can reconstruct a perfect sphere no matter what, right? You get these 2 parameters, or 4 if you X, Y, Z, and R, you're covered for a sphere. The problem is the world is not made up of spheres and planes, right? It's made out of different shapes, geometries, fine detail, and that's where it gets difficult, right? For sure, there's a surface, some parametric, high level, maybe a polynomial, maybe not, that you can use to represent this shape, right? Represent this geometry, but it gets really, really complicated. This is why the neural part kind of came along, is because before that part, people tried different functions to do it and did it to a fair amount of success. But the neural part really enabled this not endless, but very high dimensional function space that you can now use to model these complicated shapes.
Okay. That makes sense. And so is it accurate to say that, so implicit representation, because it's this function that represents it, it's a parametric model. You're moving from sort of a discrete representation into a continuous representation.
Exactly, and this is, I think, their main power here, right? Because in the discrete level, you always have like estimates of things, and you try to, even normals, right? It's a normal estimation. But if you have the continuous representation, you can compute it. There's an analytical function to compute the normals, the curvatures, all of these kind of nice geometric properties that if you have this implicit representation, they're much easier to compute.
Yeah, so this is from one of your I think lectures or presentations where you have a bunch of discrete representations of this bunny.
The Stanford bunny.
It's classic.
Yeah, classic, right? Anyone in computer vision, I recognize this, and I don't even have a degree in it. But there's these discrete ways of visualizing this object, and then I can bring on the next slide, which you're basically showing an implicit representation now.
Yeah. So it's like you're moving from like with that example of the sphere, it's like you have the perfect mathematical model for it. Like you said, I have the center, of my sphere, and then there's radius. And so I know perfectly, where every, that where the surface of that sphere is, contrasted with like a point cloud, which is a set of just 3D points. I could sample my point cloud. I could represent a sphere by 100 points or 1,000 points or 1,000,000 points, where those points are on the surface of the sphere, but that's not really the sphere. That's just a representation of it. Similar with a triangle mesh, I could say, well, hey, I could use 1,000,000 triangles to represent the surface of that sphere, but it's not actually the sphere. It's an approximation of it. It's a bunch of flat little surfaces, that are around that sphere. And so moving away from, sounds like, we're moving away from these approximations, samples, to something that is smooth and continuous, and we actually are representing where is that precise boundary between inside the object and outside the object.
Yes, that's exactly right. And this actually is another important property. You don't only get the surface itself, you usually also get like what's the inside, what's the outside, and what's the distance to the surface, right? Because these are all things that could be useful. If it's a sign distance function or an occupancy grid or whatever, like you get these kind of extra properties that you wouldn't have if you use point clouds. And also, if you think about the sphere example again, think about how many points you have to sample, or triangles you have to sample on the sphere in order to get like this nice, smooth, rounded representation, and how many parameters you actually need to store in memory, right? That's a huge difference.
So an SDF may be a term people may know or may not. So I'm looking at this I have on my screen. If you're watching the YouTube version, you get to see some pretty pictures, but I'll describe it verbally. You have basically a bunny represented as a bunch of points. Let's just say this. I think there's probably hundreds in this image I have, but let's say it's hundreds of thousands of points. Those aren't perfect, and so is SDF. Correct me if I'm wrong. Is SDF basically trying to say, okay, so some of these points lay outside, some of these points lay inside the object. It's trying to figure out where that boundary of what is actual the edge of that object, where that inside and outside of the point cloud is, to represent that object. Is that wrong? Am I totally off? I could be off.
No, you're completely on point. It's just the acronym is sign distance function, right? So if you're inside the object, you will get a negative value to the closest point on the surface, right? And you get the actual distance. And if you're outside, you would get a positive value of the distance. And the surface itself, it's actually what's called the zero level set, which is basically where the function equals zero, right? That's the surface.
That makes sense. I think Jared one time equated it to votes. If you have a lot of points on the outside, you have more votes towards it. The surface is actually further out than further in. Somewhere in there, you kind of have the average between all those points, kind of finding the signal and the noise there of where the surface is. And so you're using that. You're basically using neural networks here to determine that and represent this surface of this continuous shape.
Exactly.
So,
you get an input point cloud, you encode that into a neural network that basically every point you now give it as input, it will tell you, am I inside? Am I outside? What's my distance to the surface? Am I on the surface? And this actually allows you to reconstruct the surface using very standard ways.
Okay. Yeah. And I also have another example here where as a human, I might be able to see, I have a picture of a box with 5 points in it. As a person, I might be able to connect those dots in my brain logically to make the shape of something, but a computer will see 5 dots, and unless you give it some instruction, it just knows there's 5 dots. How do you connect them? You could connect those in quite a few different ways if you didn't have any sort of instruction. Perhaps which way are those dots pointing? Which way's out? All right. Okay, so let's jump into then. You've done some research on this topic in the last 2 years. You had a paper in CVPR last year, and you submitted it looks like a project this year. For people who don't know what CVPR is, we did an episode on that. Make sure that's linked in here. That's the premier computer vision and pattern recognition conference for computer vision scientists. And your one from last year was called DIGS. Can you jump into what problem you were trying to tackle, or your problem you tackled with INR with that project? What were you trying to accomplish with that?
Yeah, sure, happy to. So the the idea behind the Diggs paper, which is short for divergence guided implicit neural representations or surface reconstruction, um, is the fact that all of the method, well, most of the method that kind of preceded it, basically kind of set their own supervision, right? So when you train a network, right, you usually have different ways of training it. The question is always like, what data do you have? Like, what's the ground truth? What's your labels in some cases? And in order, and like for deep SDF, for example, like, which is one of the first ones, they assume they know everything. They can actually, for every point in space, you know the distance to the closest point on the surface. And this is data that in practice you rarely have access to, right? When you scan something, right, you get the point cloud, but you have to kind of come up with some way of estimating this distance, and it's not always accurate. And not only that, some methods that don't use, so some methods that came after that didn't use the sign distance function for supervision, but use the normal vectors, for example. But then again, this is another field of research where you have normal estimations and it's not always correct. And like, and ideally what you would want is you want to take your point cloud, which is like the rawest form of data that you can get from your scanner, and you want to get your surface reconstruction directly from that, right?
Mm-hmm.
And that was the starting point of Diggs. We kind of wanted to see how well can we do a surface reconstruction kind of algorithm that relies on implicit neural representations, but without those kind of extra supervision signals.
Okay. So your challenge is, and I should be bringing up this on my screen, but basically you have, in your example, a point cloud. Someone went out and it's just hypothetical. You're a surveyor and you have a point cloud of a warehouse, and somehow you've lost your normals from that LiDAR scanner, or perhaps they're just not good, and you want to use SDF to figure out, I want a geometric representation of this warehouse, and now I no longer have those normals, and that was very helpful in the past, but now you're trying to do it without. So what was the approach then you took to that you used in Diggs? If you can kind of bring as low levels or as high, I guess high levels you can for people, kind of you had this challenge, you no longer have those, what did you do to kind of overcome that issue of not having good input data?
Okay, this is going to be a tricky one. I'm going to try my best. So as high level as I can. So there are two main points there. The first one is it goes to, well, every neural network that you use kind of starts off with some initialization, right? You usually it's some random numbers that you kind of draw. And it turns out that for surface reconstruction, drawing random numbers is not the best way to start, because you start with this very weird, noisy geometry that doesn't mean anything. So one thing we did there was to initialize to a sphere. We came up with this sophisticated way where you're not starting with random geometry, you're starting off with a sphere. And starting off with a sphere is really important because you kind of just, you can imagine like pushing it from different directions to kind of match the data that you have, and then it makes the job easier. That was one aspect of Diggs. The other one, which is the divergence side of things, is basically to say, well, so mathematically you push the divergence to be as low as possible. What does that mean, right? What is divergence? Even most people that took, I don't know, calculus somewhere in the bachelor's, they don't remember divergence anymore. If you think about it, you can imagine like space having these kind of, we talked about normal directions, right? And the idea is that if you walk along a surface, the normals don't change too much, right? Imagine you walk on the plane, right? It's always pointing up. Maybe you reach the end of the sidewalk and then it's pointing in a very sharp turn, but it's not all over the place, right? It's not pointing in each and every different direction. And the idea of pushing the divergence down is basically to say, well, there is some level of smoothness that you want to keep in your geometry. And this smoothness constraint, this kind of thing that forces the geometry to be smooth, is what allows it to kind of get this first, we started with a sphere, now we're kind of pushing it to be this kind of coarse, really smooth surface around the shape, and then slowly we can remove that smoothness constraint, so it's actually like fitting the shape really well. So it's kind of this coarse to fine kind of approach. Start with a sphere, smooth it out into the shape, and then fit.
I like
Okay.
that. I like that. So it's like saying, so you first, sounds like, so you figured out how to, instead of just random initialization, just random numbers inside of this machine learning model, inside of this neural network, when it's starting to learn and train on that data, you're saying, okay, well, figured out how to do the initialization to initialize it to something that actually isn't just random, but it's a sphere, some sort of representative object, and then you have this divergence criteria in there. So some sort of constraint saying, well, hey, I expect my object initially. I'm going to constrain my object such that it's relatively smooth. I don't have a lot of jumps or noise or bumpiness in that surface. But then you were saying, this is something about like over time. So as that sphere starts to be deformed and it's closer, more closely matching the surface, then you said you can lower the that divergence constraint. So saying allow, okay, so now that we're closer to our final surface, allow it to be a little more bumpy, or allow it to better match sort of like the fine detail or the fine structure of that shape.
Yes, that's exactly right. And maybe if we want to take it a little bit more high level, I think we can imagine like a balloon, right? So imagine we have a balloon, it's inflated. We have the shape inside, right? But we start with it inflated, so we don't know where the shape is. Then I slowly start to take out the air out of the balloon. So the balloon slowly starts to fit onto the shape. And then but it's still the balloon, right? So it's like stretching over the shape and it's kind of over smoothing it because it still has some air locked up inside. And then at the end, if you suck all the air out, it kind of fits into the shape precisely.
Oh, I like that. That's cool.
Yeah, that was a really good way of describing what's happening. And then again, if you're on the YouTube version of this, I have on my screen kind of your procedure outline for training here. And again, you see it looks like a sphere, an egg almost. And then, you can see the shape kind of evolving into this dragon. I love your presentation. I'll make sure it's linked as well. Kind of like how to train your dragon. We're turning it into this model of a dragon. You can see the details popping out as the different stages of divergence here we have. It's very neat how you've tackled that. So
Thank you.
When I was first looking at this, my question was, do you get the sharp details? Because you are kind of working with, you want everything to be diverging towards a smooth surface on everything. But I know that in real life, there's lots of non-smooth surfaces. Does this not work well on, say, really high detail? Let's say I'm trying to think of something that's got a lot of sharp, pointy things like trees and tree branches. Does it do okay with that, or is there is there a limitation there?
That's a good question. We haven't tried on trees and tree branches, but it can get, well, it really depends on the capacity of your network and the amount of data that you can use. Because in the paper we kind of looked at, for example, an indoor scene which is fairly big, and you have a lot of different details, and it is mostly planar, but you have a plant in there. So and it does a pretty good job. The problem with these fine details is that actually for exactly these problems, the normal vector is actually really important because it's a very strong cue to where the surface is. Yes, this example of the scene visualization is actually a very good one, right? You can see that we're capturing detail fairly well, and the problem is, well, if you compare to other methods, if you take out the normal vector, you can see that they create these, we call them ghost geometries, like it's a lot of blobbiness all around. So yeah, and for example, you can see the plant right here where it stopped. You can see the plant at the end. It kind of smooths it out a bit. Maybe we could have trained it, for longer, use more samples on this particular area. That would improve it. And there is a way to go here, right? This is definitely not the final say as far as surface reconstructions go, but it is a step compared to like the previous works that tried to tackle the problem with this extra supervision power. But don't get me wrong, if you have that supervision and it's reliable, use it. You're probably better off. You'll get a better result. This work is basically about what if you don't have that data? What do you do then?
Right. I like that. That's that's real world. Jared is used to having to work with 3D reconstruction pipelines in environments in real world where things aren't perfect. They're always saying, "Oh, here's how to model something using photogrammetry," and they're going to show you an object in a studio lit room and all these ideal things. What do you do when you got dark shadows and crazy lighting and all these things that don't go your way? Well, this is just another thing. What if you don't have this in this supervision data? What if you don't have these things to help you in real life? That may be something that you have to face. And so I like that you guys are thinking about that. Not, oh, this is great, this is ideal, everything. Look how great this technology works. Well, that's typically not the real world. All right, for some time, you did. So this year you have a new project, OGINR.
Yes.
It's can you kind of did what we just did with digs. Can you take that kind of a high level? What are you trying to solve with that project? What's different about that versus your prior work?
Yeah. So before I say anything, I should say that this is mostly a student that I'm working with. Like he's the main author of that paper, Chamin Hewa Konputugorage. He's at the Australian National University working with Professor Stephen Gould. This is part of his PhD, and he's also a co-author on the DIGS paper. We're joint first author on that work. So in the OGINR, which stands for octree guided implicit neural representation, we take kind of a different path to solve this problem. And that path basically says, well, we know that if we have this ground truth distances information, right? We know it since deepest DF, we're getting good results. But what if we only had some level of estimate, right? What if we could have guessed it, and not only guessed it in a way that kind of is baked into some volumetric structure that could actually make things easier later down the line. So for example, in areas where you have high detail, you don't want to consider them exactly the same as very coarse, right? You want to have this kind of level of detail level of detail control within your method, your model. And the way Chamin did that was using what's called an octree. So those who don't know what octree is, it's a standard data structure that basically subdivides the space into 8 cubes. So you always subdivide the space in you split it into 2 halves in each of the dimensions. So 8, right? So you have a cube, you subdivide it 3 times, you get 8 cubes, smaller cubes, and so on and so forth, until you get like this very, very little cubes to represent very, very small portions of space. And the idea here was to kind of build this initial octree to match the based on the input point cloud, and then you kind of already have this kind of nice guess of what's inside, what's outside. It's not a good guess, it's a very rough guess, but then we had this kind of nice way of iteratively kind of going through the different volume portions and deciding, well, should this be inside, should this be outside? Because let's say you have a very big gap in your data and you're not sure, or for example, you have like a surface point, and then next to it you have an inside and an outside point. So there's probably another surface point there, right? Because inside and outside, they don't touch unless it's like a surface there. And that actually allowed the implicit neural representation to learn this nice high fidelity reconstructions without having, again, these normal estimates similar to DIGS, but it's kind of a different approach to that. It uses the data structure and the estimate of the distance.
Okay, so you're tackling some of the same problem, just in a different different strategy. And so I have on my screen as well, kind of shows the octree tree that you're describing, where you take a shape of, it looks like a part, an industrial part they have a point cloud of, and then I think I always bring down Minecraft. So if you're listening to this on the audio podcast, it's like, think of, I don't know, some sort of object on your desk, and then you turn it into 8 cubes to represent it. You would not even know what that is. Like a coffee cup in 8 cubes, you may know it's a coffee cup, but then as you subdivide those cubes down, the shape of the coffee cup starts to emerge. But the problem is those cubes can't perfectly represent the smooth roundness of a coffee cup. So now you're starting to say some of these cubes are inside, some of these cubes are outside the object, and then that'll help guide towards where the true surface of that object is. I described a coffee cup, but in this picture it's not.
That's exactly right. Minecraft is the best way to look at it. Just I guess the main difference to Minecraft is that in Minecraft the cubes are all the same size, and here you can have smaller and smaller cubes depending on the level of detail that you want. And this is like the power of the oak tree. Like it subdivides the space in a way that kind of allows you better control over your resources, like your compute resources, because you don't have to have the smallest cubes everywhere. You can have big cubes some places, small cubes other places.
Interesting. So this doesn't. I think when I first looked at this, it was everything is uniformly subdivided in the same size cubes for the representation. So you could have some parts that are fairly well represented with much more coarse cubes versus other parts that are more intricate. You would want smaller and smaller detailed cubes.
Yes, exactly.
Okay.
Yeah. This is the power of oak trees. This is why people have been using them a lot in robotics, actually, because these structures robotics are applications where you're very resource limited. Everything needs to fit on the robot, low memory, everything needs to work very fast, and oak trees have been around for a long time, particularly for that reason. You can process the different levels of detail, A, in parallel, but B, in kind of these you don't need as much compute because you don't have the full resolution. You have higher resolution only where you need it. Yeah, the example here of the Koch snowflake is a great example of that, right?
Right. Yeah, I see. Again, you see portions of the snowflake where the detail changes depending on what you're getting closer to a real surface. Here, it looks like. Any questions on this, Jared? Does that make sense to you?
I was just going to say, can you expand a bit more on, so just contrasting this with the other work, so with Diggs, saying, so before we had this sort of spherical representation or initialization, plus the divergence constraint to help constrain the smoothness as the learning progresses. Here with the octree, it sounded like the motivation for that was saying, well, if I don't have normals, if I don't know ahead of time what's inside outside, we can use the octree to help initialize, our guess about like, well, hey, this is a part of space that's outside of the object. Here's a part of space that's inside of the object, and then we get finer and finer around, more and more detail on the edge of that surface. So, are these complementary approaches? Could you use an octree supervision with Diggs, or are these two separate things?
Yeah, absolutely. You could use them. They are, on the one hand, they are separate things, but you could use them in the same pipeline. I guess one thing I haven't mentioned about Diggs is that computing the divergence takes a long time, and it makes it significantly slower to train than other methods. And this was one of the problems we wanted to solve with the OGINR paper, that we said, well, how can we do it faster, but still and take like a different path to solving the same problem of not having the supervision. Then we say, oh, okay, these oak trees, we can have a good guess of what's where, and then you kind of you get a good reconstruction, and you're faster than Diggs. But you could use them in the same method. There's no limitation on that. You enjoy both benefits, but then you kind of, it will take you longer time to process because of the Diggs overcomputation. And we were thinking of other ways to get Diggs to work faster. You don't have to compute it analytically. You probably can do some estimate, but we had to move on to the next research project.
Yeah. Okay, so talking about compute time as well. Let's say I'm looking at one of these. You're reconstructing that room that I showed earlier. Are we looking at? I think of NeRFs when they first came out. It was days. That's why I didn't really pay attention too much to it. I thought, oh boy, I can't do this at home. And now we're looking at minutes. Are these sort of training cycles really? I know it also depends on the hardware you have, but are we looking at this being fairly quick, near real time, or is this much longer training time?
Yeah, that's a good question. So Diggs wasn't, for example, oriented towards speed, and it takes, I guess, several minutes, depending on the shape, its complexity, the level of detail, and the level of accuracy you want to get in the reconstruction. But I would say minutes. There are other methods that it's called. I can't remember the full title of the paper, but for example, NGLOD that came out from NVIDIA, if I'm not mistaken, that I think can do it in real time now. So you can get an implicit neural representation, good reconstruction quality in no time.
Interesting. So and that is a good point to point out that your focus was not speed. Your focus was on other things.
It was quality.
Yeah. We've seen in NeRFs, people on quality, people on speed. Eventually, all these kind of get put together, taking techniques that other people have showed.
Yeah, that's the nice thing about academia. We can focus on whichever sub problem we want, but in industry, they need to have it all. So I leave that part to them.
Well, when you talked about robotics, I'm thinking of some sort of self-driving or self-navigating robot, be it a drone, a rolling robot, or anything like that, a car. It would need to be near real time. It would need to be real time, really, to use this. Interesting. All right, so I just want to kind of wrap this up. So now I want you to talk. We're going to have two quick questions. The first question is for an aspiring, a young Itzik who wants to go into this or wants to dabble into this technology. Is there something that they could do at home to play with it, to just kind of learn about it? Is there any software out there today that's for research use or free to use that they can kind of learn about?
Yeah, so I would definitely just start with the deep SDF paper, go play with the website, play with the code. But if you want software, then there's SDF Studio, for example, that they have a lot of implementations of state-of-the-art papers that you can kind of get your hands dirty real quick and dive into all of the issues with working examples. So that would definitely be a place to go. And then there are luckily there are a lot of resources online about all of these papers. So one of them is my personal podcast, Talking Papers, where I interviewed Chamin on our paper, but also Bacon, for example, which is another paper that has something to do with this world of INRs, and also the Poisson surface reconstruction. Like there was this new probabilistic approach that they took on this matter. So I have like this series on surface reconstruction. So if you're kind of more of an audio person, and you probably are because you're listening to this podcast, then I would definitely recommend listening to them instead or in addition to reading the paper. But definitely if you're more into, okay, let's start coding. We have our code online, by the way, for both Diggs and OGINR will be up soon. But definitely SDF Studio is probably like one of the best place to start as well.
All right. That's some good guidance there. Okay. So, I will link your podcast as well. If you're looking at the show notes, I used it to prep for this episode as well. It's a great resource for people specifically who are in academia or science who want to go a little bit deeper than we did today. And so then, okay, now I'm not in computer vision as a discipline, but perhaps I am interested. I'm listening to this episode because I want to be educated on how this technology works, because I think my business interacts with it. Is this really technology that people should be focused on today, implementing in perhaps the workplace, or is this something like, I think like NeRFs, there's not a lot of application for it yet, but it's something we shall be watching at because how much is happening in it. Is this also something that is being used today that we should be focused on, or are we a little far away from it being commercialized?
No, I think that it has applications today, right? Because surface reconstruction, people do it, right? They use Poisson surface reconstruction because it's implemented like, I don't know, all of the software that do surface reconstruction, and we show and other methods show that we can outperform Poisson surface reconstruction. So yeah, in that regard, it's definitely usable. I would say that it is still a growing field, right? There is still research to be done. There are still issues. There are still problems. We would love to have it like, as generalizable as possible, right? Like train on one data, use it on another. Right now, you kind of have to train and test on the same data. So there is work to be done, and especially I think it's going to shine in applications like, where you have a lot of intricate details that you want to reconstruct. So personal avatars, and all the metaverse kind of applications, right? So is metaverse an application? It is, right? It's happening. It's not everybody's using it yet, but if you want to stay ahead of the curve, then definitely I think this is one of the places, like this is one of the technologies that is going to be useful in it, or at least would be a building block in some other general pipeline. Yeah, and I think one of the most interesting papers that I also have on my podcast is Icon from Michael Black's group, and Econ, which is like a newer one of a newer work that kind of solve a similar problem of getting an avatar from a single RGB image.
Yeah, I'm flashing Icon on here, just some of the slides, and it's a fun one just to look at. Just thinking how that sparse set of images we're making avatars that are dancing and doing complex movement.
I think this is an interesting application because when you think about it, trying to reconstruct a person, not a static one, a dynamic one. A person is moving, their face is moving, they have different expressions, their clothes, the way they drape. These are super complicated things that you can't model parametrically if you try, with actual equations and functions. But once you encode it into a network, well, that seems to work.
Yeah. I really like all this line of work coming back just to the application of it, because it's as a goal, it's a lot of computer vision is trying to represent reality, recover from images and video from the real world. How can we digitize the real world? How can we take the real world and turn it into something the computer can understand? And so there's all these different ways that a computer can try to represent reality. It can represent reality as a picture, a set of colored pixels in an image. It can represent reality as a point cloud, so X, Y, Z, 3D points that try to represent, here's a point on the surface somewhere in reality. And then there's triangle meshes. We have NeRFs, which try to represent the visual appearance of a scene from different angles. And now with these implicit representations, and then adding the neural, on top of it, saying, okay, now it's a neural implicit representation, trying to do a better job of understanding, well, where is the surface of this, of the geometry in my scene. So it's yet another way to represent reality, digitize a world, in a very accurate and precise manner. And so it's just all of these are just different ways to digitize the real world. And so to me, continuing to make advancements in these spaces is highly relevant as we try to design algorithms and computers to do a better job of interfacing with and interacting with the real world.
Yeah, that's a good way to put a bow on this episode. It's just another, I wouldn't say it replaces, this is, to me, none of the technology that we ever look at replaces anything in the past. It's just yet another tool, and it's figuring out which tool do I need to utilize to solve whatever problem or visualize whatever environment I'm facing with the computer. How do we best tell the computer what it's looking at? So... Yeah. All right. Well, with that, I just want to thank you, Itzik, for coming on this podcast and sharing all of your knowledge on this. And as well, thanks, Jared, for joining again and providing your input from a computer vision scientist. I hope people understand this. I will ensure that at the end, I will have all of your information linked in the show notes, so people can find you, people can find your research, people can find your podcast. You have been a great resource for me and for the computer vision field as well. So I'd just like to thank you for being on this episode, and hope to see you guys in another episode on perhaps the CVPR 2024 paper. All right.
Yeah. Thank you very much. Thank you very much for having me. And thank you for this amazing podcast.
All right. Thanks.
You.
Well, that episode's a wrap. Thank you for tuning in. I hope you learned something new about implicit neural representations, as it is a quickly evolving technology that we all should be aware of. And please subscribe if you like this content, as we'll be bringing more to you every other week. I'll see you in the next episode.